Individuals and organizations stay future-ready in a rapidly evolving world. GSDC is accredited by the Accreditation Board for International Certification Bodies, ABICB. For 10 years, we've certified more than 100,000 professionals across Europe, North America, Asia, and Africa, with our offices in Switzerland, the United States, and Singapore. Our programs are recognized by leading publications and podcasts, including Forbes, Tech Target, People Managing People. We offer 100-plus globally accredited certifications across emerging and in-demand domains like generative AI and emerging technologies, HR and learning and development, project management and agile Scrum, ISO and quality management, information security. Each GSDC certification is designed to empower professionals with confidence and help organizations stay competitive in a fast-changing landscape. Every certification is crafted with insights from 100-plus global advisory board members representing top universities and leading industry experts. Our certified professionals are trusted by 500-plus multinational companies, which help unlock better roles, faster promotions, and delivering cutting-edge expertise. We partner with 100-plus authorized training partners and 50-plus universities, supporting talent across all career levels, from entry-level to executive leadership. As a GSDC member, you gain lifelong access to interactive webinars, hands-on workshops, SME panels, and global summits. Join a vibrant community of 25,000-plus members and be part of our global events. Check our reviews on Trustpilot. We're trusted worldwide for quality, support, and impact. Whether you're aiming higher or building tomorrow's talent, GSDC is your partner in purposeful growth and impactful leadership. Visit our website to explore our offerings. GSDC, share the best practices and learn from the best practices. Welcome to the Global Skill Development Council, your gateway to digital transformation. We are an independent, vendor-neutral ISO IEC 1024 accredited certification body committed to helping individuals and organizations stay future-ready in a rapidly evolving world. GSDC is accredited by the Accreditation Board for International Certification Bodies, ABICB. For 10 years, we've certified more than 100,000 professionals across Europe, North America, Asia, and Africa, with our offices in Switzerland, the United States, and Singapore. Our programs are recognized by leading publications and podcasts, including Forbes, Tech Target, People Managing People. We offer 100-plus globally accredited certifications across emerging and in-demand domains like generative AI and emerging technologies, HR and learning and development, project management and agile Scrum, ISO and quality management, information security. Each GSDC certification is designed to empower professionals with confidence and help organizations stay competitive in a fast-changing landscape. Every certification is crafted with insights from 100-plus global advisory board members representing top universities and leading industry experts. Our certified professionals are trusted by 500-plus multinational companies, which help unlock better roles, faster promotions, and delivering cutting-edge expertise. We partner with 100-plus authorized training partners and 50-plus universities, supporting talent across all career levels, from entry-level to executive leadership. As a GSDC member, you gain lifelong access to interactive webinars, hands-on workshops, SME panels, and global summits. Join a vibrant community of 25,000-plus members and be part of our global events. Check our reviews on Trustpilot. We're trusted worldwide for quality, support, and impact. Whether you're aiming higher or building tomorrow's talent, GSDC is your partner in purposeful growth and impactful leadership. Visit our website to explore our offerings. GSDC, share the best practices and learn from the best practices. Welcome to the Global Skill Development Council, your gateway to digital transformation. We are an independent, vendor-neutral ISO IEC 1024 accredited certification body committed to helping individuals and organizations stay future-ready in a rapidly evolving world. GSDC is accredited by the Accreditation Board for International Certification Bodies, ABICB. For 10 years, we've certified more than 100,000 professionals across Europe, North America, Asia, and Africa, with our offices in Switzerland, the United States, and Singapore. Our programs are recognized by leading publications and podcasts, including Forbes, Tech Target, People Managing People. We offer 100-plus globally accredited certifications across emerging and in-demand domains like generative AI and emerging technologies, HR and learning and development, project management and agile Scrum, ISO and quality management, information security. Each GSDC certification is designed to empower professionals with confidence and help organizations stay competitive in a fast-changing landscape. Every certification is crafted with insights from 100-plus global advisory board members representing top universities and leading industry experts. Our certified professionals are trusted by 500-plus multinational companies, which help unlock better roles, faster promotions, and delivering cutting-edge expertise. We partner with 100-plus authorized training partners and 50-plus universities, supporting talent across all career levels, from entry-level to executive leadership. As a GSDC member, you gain lifelong access to interactive webinars, hands-on workshops, SME panels, and global summits. Join a vibrant community of 25,000-plus members and be part of our global events. Check our reviews on Trustpilot. We're trusted worldwide for quality, support, and impact. Whether you're aiming higher or building tomorrow's talent, GSDC is your partner in purposeful growth and impactful leadership. Visit our website to explore our offerings. GSDC, share the best practices and learn from the best practices. Welcome to the Global Skill Development Council, your gateway to digital transformation. We are an independent, vendor-neutral ISO IEC 1024 accredited certification body committed to helping individuals and organizations stay future-ready in a rapidly evolving world. GSDC is accredited by the Accreditation Board for International Certification Bodies, ABICB. For 10 years, we've certified more than 100,000 professionals across Europe, North America, Asia, and Africa, with our offices in Switzerland, the United States, and Singapore. Our programs are recognized by leading publications and podcasts, including Forbes, Tech Target, People Managing People. We offer 100-plus globally accredited certifications across emerging and in-demand domains like generative AI and emerging technologies, HR and learning and development, project management and agile Scrum, ISO and quality management, information security. Each GSDC certification is designed to empower professionals with confidence and help organizations stay competitive in a fast-changing landscape. Every certification is crafted with insights from 100-plus global advisory board members representing top universities and leading industry experts. Our certified professionals are trusted by 500-plus multinational companies, which help unlock better roles, faster promotions, and delivering cutting-edge expertise. We partner with 100-plus authorized training partners and 50-plus universities, supporting talent across all career levels, from entry-level to executive leadership. As a GSDC member, you gain lifelong access to interactive webinars, hands-on workshops, SME panels, and global summits. Join a vibrant community of 25,000-plus members and be part of our global events. Check our reviews on Trustpilot. We're trusted worldwide for quality, support, and impact. Whether you're aiming higher or building tomorrow's talent, GSDC is your partner in purposeful growth and impactful leadership. Visit our website to explore our offerings. GSDC, share the best practices and learn from the best practices.
Hello,
Welcome to the
everyone.
Global Skill Development Council.
I'm sorry about that. Yes, hello, everyone. We'll be starting a session shortly as more participants are joining us. So stay tuned. Thank you very much.
Your gateway to digital transformation. We are an independent, vendor-neutral ISO IEC 1024 accredited certification body committed to helping individuals and organizations stay future-ready in a rapidly evolving world. GSDC is accredited by the Accreditation Board for International Certification Bodies, ABICB. For 10 years, we've certified more than 100,000 professionals across Europe, North America, Asia, and Africa, with our offices in Switzerland, the United States, and Singapore. Our programs are recognized by leading publications and podcasts, including Forbes, Tech Target, People Managing People. We offer 100 plus globally accredited certifications across emerging and in-demand domains like generative AI and emerging technologies, HR and learning and development, project management and agile Scrum, ISO and quality management, information security. Each GSDC certification is designed to empower professionals with confidence and help organizations stay competitive in a fast-changing landscape. Every certification is crafted with insights from 100 plus global advisory board members representing top universities and leading industry experts. Our certified professionals are trusted by 500 plus multinational companies, which help unlock better roles, faster promotions, and delivering cutting-edge expertise. We partner with 100 plus authorized training partners and 50 plus universities, supporting talent across all career levels, from entry level to executive leadership. As a GSDC member, you gain lifelong access to interactive webinars, hands-on workshops, SME panels, and global summits. Join a vibrant community of 25,000 plus members and be part of our global events. Check our reviews on Trustpilot. We're trusted worldwide for quality, support, and impact. Whether you're aiming higher or building tomorrow's talent, GSDC is your partner in purposeful growth and impactful leadership. Visit our website to explore our offerings. GSDC, share the best practices and learn from the best practices. Welcome to the Global Skill Development Council.
All right, we'll be starting the session now. Just allow me to share my screen again. Hope my screen is visible to you all. Thank you very much for joining for today's session. I welcome you all to Global Skill Development Council's GSDC Certified Learning, Mastering SRE for Scalable and Resilient System, with the theme that is driving reliability and scalability with SRE best practices. And we have this incredible panel of speakers aligned for this entire webinar series, which is started from 1st September until happening till 12th September 2025 with the time slot that is 8:30 a.m. CST. So please do join us for our this entire week session, which is scheduled as we have this incredible panel of speaker aligned for this series. And today we'll be having Salim Virji with us. He's a site reliability engineer at Google, and he'll be presenting the topic that is building and managing scalable distributed systems. So before I could hand over the session to him, I would like to introduce our hosting organization. We known as Global Skill Development Council. We are vendor agnostic, vendor neutral. We are globally recognized certification body, and we are accredited by NSI and ABICP. We have a 100 plus certification portfolio, and we have certified 250,000 professionals worldwide. We have 500 SMEs. Those are subject matter expert, industry experts. They work with us closely to design our deliverables, and they're affiliates from top universities like Harvard, Stanford, and MIT. We are associated with 1,000 multinational corporates and 500 Fortune companies and 50 plus universities across the globe. And I'm very proud to inform you all that we do have 100 plus authorized training partner across the globe. We have partner in Asia, Europe, Africa, Canada, and many other countries. So would love to thank you those who have joined us through our training partner channel. If you're looking for any training program for yourself, I have shared the link in the chat box. You can get in touch with the training partner to inquire about the training programs that you are looking for. So a special thanks to our official media partner, World Racer, for covering all our events and press releases. So as I mentioned earlier in the previous slide that we do have 100 plus certification portfolio with us, which includes certification on generative AI, agentic AI, learning and development professionals, ISO related certifications, generative AI in cybersecurity, risk and compliance, PMO professionals, and generative AI in project management. So if you're looking for any of these certification for yourself to upskill yourself, you can definitely check out our website, that is www.gsdcouncil.org, to get more information regarding this. Also, you can get in touch with our learning advisor to get more information and assistance regarding these certifications. If you get certification through GSDC, that will give you lifelong membership. With that, you'll be getting certificate upgrade and you'll be having access to all our events, workshop, boot camps, and guess what? You'll be having access to all our exclusive learning programs that we do offer. And along with it, you'll be getting implementation resources, speaker invites, and access to all our newsletters. So do grab this opportunity, sign up yourself for this amazing certifications program. So without any delay, I would love to tell you all more about our today's speaker, and it's my absolute pleasure to welcome Salim Virji, a leader in Google's Site Reliability Engineering organization. Salim has developed reliable engineer practices, built consensus and storage services for Google's infrastructure, and co-authored well-known books such as the Site Reliability Workbook and Implementing Service Level Objectives. His expertise spans distributed system, machine learning, and advancing reliability practices at scale. So we are truly honored to have him with us today to share his insights. So please join me welcoming Salim Virji. The virtual speaker is over to you now, Salim. Thank you very much.
Thank you, Pritam, for that wonderful introduction, and I'm very happy to be presenting to you all today as part of GSDC. And my topic specifically today is patterns in reliability. And we're going to talk about how patterns provide a mature and sophisticated approach to building and managing reliable systems. So we'll look at some patterns. We'll talk about why these patterns are significant and how each of these patterns supports reliability in a production environment. Oops. So patterns, without question, are all around you in software. In fact, they're all around you everywhere, virtually and in the built environment. Patterns are also present and important in systems of software. Today, we're going to take a look at how to identify and apply patterns so that your systems are more reliable. We're also going to talk about why these patterns are significant for designing reliable systems. And reliable systems mean a couple of things. These reliable systems will be easier to operate in addition to being easier to build, and they will deliver what the customer expects. And for all of you in the audience, I expect that this is critical to why you're here, that you want to understand how to build systems better so that they provide easier, more reliable operational attributes and can get what your users need very reliably. I asserted that patterns are all around us, and part of that assertion is built on the history of talking about patterns, about the patterns in our built environment, that is the physical infrastructure of our lives, all the way through to the software we use, the software that provides underpinnings of our cloud systems, as well as the applications that we run on various devices. And these devices are smart devices. They might be thermostats. They might be game consoles, or certainly the applications that you're running on tablets and phones and TVs. And we're going to take a look at how we can identify and use specific patterns in order to build more reliable systems. And the books on this slide give you a couple of significant examples of patterns and and provide some of the foundation for why we're going to talk about patterns in big production systems. The leftmost book, A Pattern Language, and I want to emphasize the word language here. In this book, Christopher Alexander, a practicing architect, introduced the use of patterns as a way of describing the functions on buildings and urban elements. And these functions include windows and doors and vestibules, the almost atomic components that we see in vernacular architecture around the globe. Not all buildings will have windows, not all buildings will have doors that look the same. Some might be arched, some may be double doors. However, fundamentally, there are doors, there are windows or openings, and these are both functional and aesthetic. Christopher Alexander's book focused on these buildings, on urban elements, and allowed architects and laypersons alike to understand how these elements serve a specific purpose. And we'll talk about that in the context of production systems. Christopher Alexander's books also provided a way to bring these components together to build increasingly complex, yet still understandable systems. And that's really important for us as engineers who are building digital services, that we want to be able to work with components that are reliable and understand how to compose them into bigger systems that are also reliable. The center and rightmost book on this slide are a generation apart. The Design Patterns book in the center was published in 1994 or 95 and brought the idea of patterns to reusable software components. And some of these are going to reappear in the slides that we see today. And then finally, Umesh Joshi's book on patterns of distributed systems truly brought the idea of patterns to contemporary, very large-scale software systems and is the nearest antecedent to what we're talking about today. Briefly, an overview of how we're structuring the talk. We're going to identify some common patterns. We're going to give names to these patterns. Some of them are new, some of them are old in the sense that they were described in one of the books that you saw on the previous slide. We're going to understand practical and also problematic applications of these patterns. Just because you have a pattern doesn't mean that you can take it and use it in any system, or even you can take it and use it, excuse me, as you're developing the system initially. Some patterns are best applied after the system has already been deployed. We're going to connect the use of these patterns, or the successful use of these patterns, with improved software reliability. And then we're going to look at patterns from a systems perspective. Finally, there'll be time for questions and answers. I encourage you to ask questions through the social media channels or in the chat for this session. And our moderator will collect them and I'll answer them in one go at the end of today's session. Excuse me. So I'm going to start with a quotation from the first volume of the Pattern Language for Distributed Computing series. And this wasn't one of the books I showed in an earlier slide. However, the work is critical to understanding patterns in practice. And the quote is that patterns help you build complex and heterogeneous software systems. Well, let's keep that in mind as we go through this today's session. You will almost certainly know some of the patterns that we're going to identify. Some come from well-established concepts from the books that we showed on the preceding slide, A Pattern Language by Christopher Alexander, or the Design Patterns, also known as the Gang of Four book. Others emerge in distributed systems. And the word emerge is something that has a couple of meanings for us today. Here I'm saying that this is a finite and scoped, something becomes apparent. There's also emergent behavior, and there's the same root, emerge. And emergent behavior is how a system, once it has been deployed and it's receiving and responding to live, real user requests and actual production traffic, emergent behavior is how that system functions in the real world. This may be profoundly different from how it behaves in a test environment or in a sandbox or even in production before it began receiving actual user traffic. So there are patterns that emerge in distributed systems. And even though a lot of my experience has been with these patterns in Google's production systems, however unique those systems may seem, these are absolutely all patterns that you and I will see elsewhere in software and in systems of software. So there are three patterns that we're going to start with. They're the circuit breaker, the bulkhead, and the strangler fig. The circuit breaker may be familiar to you from computer science or from electrical engineering, or dare I say it, even from common sense. It is possibly something that you could design from first principles. And this pattern relies on, for a distributed system, this pattern relies on a communication channel. And that communication is the bidirectional messaging that passes between the components within this system. And that's a many-to-many relationship. So almost all the components are going to have message channels open with the other components. Within Google, we have a system called Stubby. This has been made available in an open source project known as gRPC, and it's a message passing system that allows us to send very efficient messages between components and also to invoke functions using remote procedure calls on remote computers. And the requests also allow for the system to provide and use metadata about the state of the channel and about the state of the different endpoints in the system. And I've been using the word system a lot. A system is a set of software, and it's dynamic. It may have this emergent behavior that I mentioned a moment ago. And that's because as systems come together, the way that they interact and the way that they behave is inherently chaotic. And so some of this behavior is not predictable. It's not stochastic. And things may happen that rely on volume or frequency of requests that were not apparent during the development or testing. And this is where a circuit breaker can be extremely useful, because even if you have designed the system to handle a wide band of traffic and to have functionality that puts in safeguards at an upper bound, even before the system reaches that upper bound, or as it reaches that upper bound, its behavior may change. Congestion on the communication channel or unexpected delays in message processing may contribute to different behavior and possibly quite worse behavior. The circuit breaker pattern provides a way for the system to fail or shut down without suffering too much damage. Ideally, it suffers close to no damage. And by damage, we mean either that the system exhausts its available resources and becomes unavailable in a way that manifests as a crash or a stall requiring operator intervention. And you don't want that, because that's expensive. It's expensive to diagnose, it's expensive to remediate, because someone, a human, needs to get in there and make a change. So you don't want that kind of damage, because it's expensive and difficult to operate. You also don't want damage in the sense that user requests, legitimate production traffic, might be passing through the system and then go unanswered or unacknowledged because the system got into a bad state. So the circuit breaker appears in a default closed state. And during this closed state, the circuit is closed. That means requests flow through the system. And as new requests come in, they go to the various downstream components or backends where the response to the request is generated, and then the response goes to the end user. That end user may be a person, it may be another computer. In the half-open state, requests continue, and then they're specifically evaluated to ensure that the system is able to respond without becoming overloaded. And this is where metadata in the channel becomes important. The downstream parts of the system are able to, with each request, respond to the originator that yes, they're still able to accept new requests, or no, they are approaching a threshold for being overloaded and cannot accept new requests. In addition to what's in this communications channel, the communication infrastructure can also evaluate the time for each response. And if that time deviates, maybe by 1 or 2 standard deviations from the norm of the response for that request, then the traffic control can break open the circuit breaker and allow the system to refuse new requests. Now, when the system is in this open state, it's not taking additional traffic. We'll talk more about what happens there in a moment. And typically there's a timer or a specific threshold that needs to evaluate before the system will return to the closed state. So when the system is refusing no requests, I think this statement brings up a lot of implementation questions. What does that look like? Because the system, it's fine for me to say, okay, the system's not taking any new requests. So for a human user, you usually want to tell them that the system encountered an error, it's going to try again. So you want to tell them the state of their request as well as what's going to happen next. For a computer, you want to do the same thing. So that is, if there's not a person at the other end of this request that's being denied, but a computer, you want to tell that originating program, I didn't process your request, try again in some number of milliseconds or some number of seconds. And you can retry up to this many times. And there's a it's very important to have this programmatic interface so that the program doesn't keep retrying, which is the human equivalent of hitting Control F5 until that browser page loads, because that's only going to add to the number of messages that are in a deferred or retry state and could lead to other problems within the system, such as cascading failure. Now, circuit breakers appear in various forms. Many of them are as fundamental and straightforward as what you see on the screen here. Sometimes they're more complex. The mode in which the node servers in Bigtable, Google's cloud NoSQL service, in which those node servers express the open state, is called pushback. And in this state, the node servers use metadata in the communication channel to indicate that they're on the verge of being overloaded and cannot or can no longer accept a client request for processing. Other forms are more simple, such as the load balancing techniques that use real-time load information from downstream systems in order to decide whether or not the circuit to those backends is closed or not. However, I want to warn you against using a circuit breaker prematurely in the request flow, because that can result in stranding resources. Now, picture this. You've got a circuit breaker, and the circuit breaker is configured to trip open at a certain threshold. But this threshold was not actually evaluated under production circumstances. So the circuit breaker trips open, and traffic is no longer going to the backends. The backends, however, were not only not overloaded, they are entirely capable of providing all the responses to the requests beyond the level at which it was configured. Now the system is not servicing requests, and the backends are not doing any work at all. So those resources have been stranded. And this is why it's important to understand the production behavior of a system, possibly before applying the solutions such as a circuit breaker. That is to say, you can build the circuit breaker and you can have it in place, but you can have it as a no-op until you understand and can defend the thresholds that you're setting for that circuit breaker. And of course, there are sophisticated approaches such as dynamically setting the thresholds or using feedback from the backends or downstream nodes in order to determine what that threshold should be and allowing that to change as the resources in the backend themselves change or as traffic patterns change. And again, this would be a response to emergent behavior in the production system. So that's the circuit breaker. Now we're going to look at the bulkhead. And again, this pattern draws its name from something in our actual physical environment. The bulkhead is the name for the physical compartments in maritime vessels. And these are watertight compartments below decks. designed such that the failure of one does not cause the entire ship to fill with water. And you can see that in the bottom left of this slide, there is a schematic or blueprint of a 1920s era passenger vessel. This is something where there are a lot of people and passengers and staff throughout the ship. They're also just below the waterline traversing both above and below the waterline and all the way down to the keel are these big compartments. And these compartments are sealed against each other. So they're discrete. There is no passage between compartments. And the idea is if a ship is holed below the waterline, say by a cannon or an iceberg, the bulkhead immediately where the rupture or hole occurs, that bulkhead might fill with water. Yet not all of the compartments fill because, recall, there's no way to get between these different bulkheads. So one bulkhead fills, but the ship's engineers knew that if one bulkhead filled with water, it wouldn't cause the ship to lose balance, it wouldn't cause the ship to capsize, it certainly wouldn't cause the ship to take on additional water, only as much as that single compartment would hold. Of course, the Titanic provides a very unhappy counterexample to this because either the design was flawed or in practice, something terrible went wrong. In our vernacular, the bulkhead pattern allows traffic, that is a set of requests from users or consumers of the system. This traffic will fill a set of backends, and these backends are analogous to a bulkhead. Yet this traffic will not necessarily overflow into other backends. And at Google, this is so fundamental within our production infrastructure that many engineers might not even know they're using it. It is a principle of our production infrastructure, and it was informed by the need to defend against cascading failure. And cascading failure is the notion that when a problem or issue affects a set of backends within the system, a set of backends representing nodes that are responsible for doing some work and passing it along to the user or to other parts of the system. When one of these backends fails for some reason, we want to make sure that other backends in a similar position do not fail for the same reason. And in the schematic that takes up most of this slide, you'll see A, B, and C, which represent consumers or the first level of request originators. And these are sending traffic to the middle row, which is labeled primary worker pools. Each of these worker pools represents several, maybe tens, maybe hundreds, maybe thousands of servers that are all doing the same thing. They're all processing the same class of requests. They might be web servers, they might be middleware servers, but they're all doing essentially the same work. Again, each of these pools is analogous to a bulkhead. And if one of them fails, we don't want the spillover traffic to go to another one of these primary pools and cause it to fail for the same reason. And that reason might be something as unique as what we call a query of death, something that is malformed or so resource consuming that it causes all of the compute resources available within that pool to lock up. We don't want to pass that same query onto another pool. So we either isolate it or we drop it or we allow our traffic management system to do something such that the bad request is ignored or dropped on the floor, and then other legitimate traffic can continue to the backup pools of worker nodes, which are on the bottommost row of this slide. The bulkhead pattern has inspired auto-scaling in specific Google systems such as Cloud Run. And the features that it inspired are essential for providing the always-on services that thousands of Google Cloud business customers use for their own business-critical applications. And the feature allows the service to protect core resources, which are vital to ongoing customer demand, and also to provide headroom in which customer applications can grow. And the way that this application of the bulkhead pattern works is that the baseline capacity that services need is isolated from additional capacity for organic growth, for spikes in traffic, or for new applications to be deployed. So there's this baseline of regular daily traffic, and the system has some component, or the Cloud Run system has a component which is evaluating and setting these thresholds regularly so that we know to set aside and isolate in a bulkhead the resources that we need to run all of these customers' business critical applications. Then there are separate capacity pools, different bulkheads that provide more capacity for handling traffic spikes. And these also support new applications and address emergent behavior. If an application becomes much more popular from one day to the next, this is organic growth. It's different from a traffic spike, which is, back in my day, also known as a slash dot effect, where many times the usual number of visitors would go to a website or application. So this use of bulkhead is an inversion of what you saw in the initial description of bulkheads. In this case, we're using the bulkheads to protect outbound resource flow. And this way, requests that are intended for the baseline capacity are protected. And then there's a separate compartment with additional capacity that can be opened or made available when there is greater demand without affecting the baseline capacity. And then the bulkhead and circuit breaker, the pattern we saw a moment ago, are often used together to provide fine-grained control over the flow of request traffic through a system, and together provide defense in depth by controlling both availability of resources and access to these resources under duress. The next pattern we'll take a look at is the strangler fig. And many of you will know this, if not by name, then by its description. Let's suppose that your project is to move a working product or digital service from one platform, framework, or system to another. Typically, this begins with the intent to transform a monolithic system or an existing yet outdated system. As you see in the schematic on the left, it's just one big blue box. Components or features within the original system become new components or microservices in the new system. And the middle box shows this hybrid state where some new components are running within the overall system. The end state appears on the right, where all new microservices have replaced the original system entirely. You won't always be replacing a monolith with microservices. You might be moving from one generation of microservice components to another. You may not be replacing the entire thing, and you may just be replacing some services. You are using the strangler fig pattern. The name comes from a description by the software developer Martin Fowler, who was inspired by a fig that germinates in the upper branches of trees. This fig is epiphytic. It does not need to root in soil. The existing tree, and you can see the life cycle on the bottom left here, the existing tree becomes a support structure for the growing fig plant, which extends its roots to the ground and surrounds the tree itself with fig leaves and new branches of its own. And this is where the strangler part comes in, because the fig's leaves absorb all available sunlight, denying resources or traffic to the original tree. And the fig takes resources away from the host tree. Eventually, this host tree withers, leaving only the trunk, which eventually also decomposes. Finally, only the new, entirely self-supporting fig remains in its place. And this transformation, while parasitic, is a nice analogy for the process of replacing one set of components within a system with a new set. And we often see this pattern in practice as we replace existing systems. Sometimes it's converting a monolith to a set of microservices. Other times we're replacing deprecated systems with new microservices. At Google, we had a moonshot project to move from one generation of distributed storage, which was the Google File Service, or GFS, to the next generation. And we followed this pattern, eventually replacing the original storage system, GFS, down to its very roots. We wrote a short book about this, this appeared as one of the case studies in our book, Case Studies in Infrastructure Change Management, which is available for free from the Google SRE website. And there's a link at the end of this presentation to where you can find this. And what we learned was that, yes, this is possible. Yes, plenty of people and projects have done this before, and it needs to be approached very carefully. The strangler fig pattern leads to, when done correctly, leads to more reliable systems because it supports the process of iterative migration from one system to another. And this enables you, or in the case of our moonshot project, enabled us to replace pieces in discrete testable stages rather than moving the entire system from 1.0 to 2.0, which many of us know from experience is an almost insurmountable challenge. And in the case of a storage system, moving all at once would have meant copying all of the data from the original system's format to the new system's format, which would have meant having twice the storage that we actually needed, which would have been extremely resource intensive, which you can also hear as expensive. And even when this took place 15 years ago, at the scale Google was operating, that was probably the largest storage system in the known universe. So we definitely had benefits from doing this in stages by moving through a hybrid stage and eventually over a couple of years to the point where the replacement system had completely taken over the original system. And while this example that I'm using may be a little extreme, because I've certainly worked on replacements that were smaller in scale, yet also profoundly challenging, the strangler fig does need to be approached with a lot of humility, and it provides very useful structure for moving from one system to another. And yet it will also require careful project management. I encourage you to take a look at the Case Studies in Infrastructure Change book because it does call out some of the issues around managing and executing on migrations such as this. The next pattern we're going to look at is the lovably named half-sync, half-async pattern. And this pattern emerged from research jointly undertaken by folks at the University of Washington, St. Louis and UC Irvine, both in the United States, in the early 1990s. And it expanded, late 1990s maybe. This research expanded to include other academic and private institutions, and eventually the project became known as PLOP, or Pattern Languages of Programs. In the generations of programming since, we've identified ways that these patterns apply to programs in a massive distributed environment as well. So the half-sync, half-async pattern was subtitled An Architectural Pattern for Efficient and Well-Structured Concurrent I/O. Whew, that's a mouthful. It describes the approach of decoupling synchronous program communication in order to encourage both execution efficiency and to support concurrent programming models. This pattern is crucial for building robust distributed systems that can handle partial failures. Okay, so what do we mean by robust distributed systems? Distributed systems are systems where you have different components that may grow independently of each other, that may operate and be configured independently of other components, and especially where you will have dependencies of your dependencies. So you may not know all the nodes that your system depends on because they are either opaque to you or your system is not sufficiently well documented. We'll talk more about that too. And when we say massive, massive is very subjective. For our purposes today, we're just going to say it's more than a couple hundred computers. And computers, again, is becoming a pretty vague word. It can refer to virtual machines, it can refer to physical machines. I will leave that up to your imagination today. Just know that we have hundreds of them, and that is our representation. Well, let's say thousands. That'll be our representation of massive today. So you have thousands of computers all running some number of shared multi-tenancy programs, and they're in a distributed environment where not all of them have full knowledge of each other, yet may depend in some way on each other. The complexity inherent to asynchronous programming is driven largely by, because it's driven largely by interrupts. And this approach becomes even more fraught when it's combined with the synchronous programming model, which is I/O driven. That means there are specific points within program execution for synchronous programs where the program waits for input from the user and then processes that input. Whereas with async programming, user input can come at any time. It can be queued, it might be processed just as it arrives. There are all sorts of decisions that an asynchronous program needs to make, sometimes all at the same time as it is running. And if we want to get even more multidimensional about this, in a distributed program, there may be multiple nodes of the same asynchronous program running, and they will need to coordinate with each other which node is taking which actions so that they don't unintentionally trample each other. So this model of asynchronous program has become vital for the development of the large distributed systems that we use in many production environments today. And in one of these distributed systems, a program might need to call a service on a remote machine. You may recall from our first pattern that there are systems that we use for passing these remote procedure calls to other machines. A synchronous call would block the program's execution on that destination machine until the originating machine receives a response. In contrast, an asynchronous call will allow the program to continue executing other code immediately. So the program on the destination machine receives the request for some part of its program to operate. It can enqueue that request, it can decide how long it can remain on the queue, and it can even have multiple queues, perhaps a different queue for each method or function that's being called. When the remote service responds, it can provide a callback or a promise in order to handle the result. This prevents that program from being tied up waiting for slow network I/O. So what we're doing with this pattern is providing the most efficient way for all of the nodes to interact with each other. Each node can make decisions about how it wants to handle requests that it receives. The different requesters in this system can provide information about the priority, about the terms under which they need a response. So if they need a response within 500 milliseconds, they can indicate that in the request metadata. And the program where the data is being requested or where the method is being requested, if it cannot fulfill that 500 millisecond deadline, it can let the originator know. In this way, asynchronous communication can be more resilient to failures. And the illustration on this slide shows how a message queue, we've almost all certainly used one of these, and certainly we've depended on them for a system we've built, can use this pattern for improving reliability. So this way, if a remote service is down, that is a service that's running on some other node in this distributed production environment, if a remote service is down, your program doesn't get stuck indefinitely. You can have your request time out. You can try an alternative, such as another backend running the same service, or you can log a failure and move on if possible. Now let's suppose a message queue in our example on the screen does not use this pattern, and clients could only communicate with the message queue using a synchronous API. Now this would change the shape of resources required to run the message queue system, because the message queue would need to have enough memory, enough network in order to handle all of the requests within a certain time window. In addition, it may require additional requests for processing and managing a queue. In turn, using this pattern, that would be suboptimal because you'd require more resources. You would almost certainly also be using those resources less efficiently because blocks of resources would be allocated statically to handle requests. In comparison, if you were handling the requests asynchronously or doing some dynamic processing based on priority, then you could free up network queuing space, memory space that would use for processing, either for other programs to run or for your program to run in multiple instances. So this pattern supports reliability by supporting partial failures. Some traffic can continue to flow through the system, even if resources become overwhelmed or if the message queue fills up. An example from Google is the Chubby lock server, which provided this early on in its deployment as a piece of Google's critical infrastructure. Now, Chubby as a lock service allowed for important synchronous requests to continue, while dropping or dynamically changing the priority of asynchronous requests based on available memory and headroom. All right. Now we're going to get into a couple of patterns that will sound familiar, but have not been named formally in the literature yet. The first of these is graceful degradation, and the illustration on the screen shows what's called a run-flat tire. And this is a relatively recent development in tire and wheel technology. And I know that I'm opening myself up to all sorts of "you don't need to reinvent the wheel" jokes. However, this is a significant enough advancement and a good metaphor for graceful degradation that I'm going to spend a moment describing it. A traditional wheel has a rim at the center, which attaches to the axle on which the vehicle operates. And on this rim is an inflatable rubber tire. And if the tire is punctured, the vehicle will almost immediately lose stability, traction, and ability to steer because the air or other gas inside the tire provided a lot of the control surface for the wheel to operate. With a run-flat wheel, in addition to the rim, there are what you call there's an internal support ring. And so even when the tire has suffered a puncture, the internal support ring provides enough stability and structure for the wheel that can continue to operate, although at a slightly lower overall speed. It will continue to provide the stability, steerability, and traction that the original wheel and tire did. Now, this is important because the car is still operational. It's doing what it intended to do, which is presumably going from point A to point B. Yet one of its key features has degraded. That is, the inflated tire is no longer available. You're no longer able to move as fast as you originally were, but you're still able to make progress in the direction that you expected. And that's an example of graceful degradation. Graceful degradation may be, of all the patterns that we talk about today, the pattern that most clearly supports reliability. I mean, reliability is right there in the name when you say graceful degradation. So it allows purposeful systems, and we're going to talk about those in a moment. It allows these systems to continue to provide service to the majority of their clients, even when their dependencies or internal components are not functioning properly. It's what's known as a decorator pattern because it can be implemented in many different ways. You will see it used in microservice meshes as well. And graceful degradation almost always accompanies other patterns. Now, if your system has a dependency, and at Google it almost certainly does, but in most production environments you'll have many dependencies on identity systems, on storage systems, maybe on queuing or message passing systems. Graceful degradation allows you to turn hard dependencies into soft dependencies. for example, by using half sync, half async, which we just described, to accomplish this by incorporating timeouts in your message passing. One example that comes to mind in actual computer systems, not automotive systems, is for a pipeline that's building machine learning models. Creating a tighter feedback loop between different stages of the pipeline using asynchronous calls for observability will almost certainly improve the end-to-end performance of the pipeline, because the observability will be or any changes in behavior will be manifest earlier in the pipeline. So you have this tighter feedback loop, and you increase visibility into what your pipeline is doing. Rather than having an end-to-end set of observability metrics, you might have stage by stage or even intra-stage metrics. Similarly, in the concept of graceful degradation, maybe 30 years ago, we had the age of dial-up network connections with very limited bandwidth. And at the time, we had multiple tools to transfer and display images, which were an order of magnitude greater than the text accompanying them, very certainly on a 1990s era web page or bulletin board. And this led to the development of tools such as progressive JPEGs, which transferred with increasingly high resolution as more bits went over the wire. So you'd get a low resolution to start with, and the transfer of that image would continue until the full resolution image became available. And this was different from getting the image from top to bottom, where you could see line by line the image resolve, which is less useful for understanding the image in its context than even seeing a low resolution image. Similarly, the image tag in the HTML of a web page could specify what was called the low source attribute, which specified an initial icon or a low resolution image that would ultimately be replaced by a full resolution or larger sized image once the transfer completed. Something more contemporary, something that is in our current experience, is the dynamic resolution of YouTube video playback. The YouTube video player adjusts its quality based on available bandwidth, as well as optimizing for viewport, smoothness, and other factors. And our ability to name and describe a pattern of graceful degradation comes from distributed systems research and applications. And that's the part of computer science that brings us big systems with interdependent components and far-flung dependencies. And one of the themes that that might be becoming apparent in many of these patterns is that in order to provide reliability, in order to build and operate systems that are reliable at scale, you will sometimes need to sacrifice some traffic in order to save the system. And there are a lot of examples about this that I'm still developing, but the bottom line is it is almost always better to drop some requests while responding to others and allow the system to continue operating at a degraded state than to stop the system from operating entirely. And that is a foundational idea behind graceful degradation. And that is the time and time again, I've found in my experience that functioning worse is better than breaking entirely. Again, I'll draw an example from YouTube. The YouTube streams, they might downgrade quality depending on available bandwidth, but the YouTube client interface will also change how it behaves if there are dependencies that it has that aren't working correctly. It prioritizes loading the video and loading ads before loading less critical information, such as like counts or related videos or even comments. And this notion of prioritization in what happens within an application is also a way of controlling the amount of load that comes in, because if you can excise the time that you'd be waiting for your backends to send you comment counts or comment content or related videos, you can still get the user the fundamental part of their experience, which is that video they want to see. And then you can later defer the loading of these other less critical components. Another idea behind or related to graceful degradation is to spend money to add redundant backups. This is really key if you're working with any sort of persistent data or data at rest, because that data is only as good as the backups and restore process that you have. Make your process easy, test it for accuracy, and remember that having multiple backups will save you when it is most critical. Save you and your user data, that is. And that brings us finally to the purposeful system, which is the final example of a pattern that we'll look at today. And again, is a novel pattern that we're bringing to you today. And a purposeful system is going to do one thing and do it well. This will sound a lot like a microservice. There's a little more that's happening with a purposeful system. And well, now that we've established a language of patterns and we've recognized what problem each pattern can apply to, patterns such as circuit breaker and bulkhead, we can use these patterns to add to or modify our system. But we also want to have high-level patterns to think about our systems more clearly or to learn about best practices. And the purposeful system is saying things like every system needs to have a purpose. Okay, that's evident in the title, and it's a pretty obviously true statement, which leads into when we're working on building our systems, we should have their purpose in mind. We should add things, components, dependencies, functionality within the core system that keeps their purpose in mind. We should add things that help that purpose, and we should not add things which are outside of that purpose. So a purposeful system is something that has scope, that has boundaries. But looking at the systems around us, how many of them have clear and straightforward purposes? Are these purposes written down? Are they well documented? Are they accessible both to a human reader and to consumers of the system through an API? Past the very first design phase, how often do we make sure that our systems are written towards their purpose? Now, purposeful systems are the goal of software development. A purposeful system may be implemented by absolutely any means, by any mechanisms. By retaining the property of purposefulness, the most appropriate implementation may be selected, and you can thus avoid a clash between purpose and technology. However, a purposeful system is a fractal thing and will be composed of purposeful subcomponents as appropriate. And in the illustration we have on the screen, we have a box containing the Google Shoe or G Shoe. This is a telemetry-equipped smart shoe. It allows the shoe wearer to interact with an app on their smart device that records their walking speed, distance, duration, how balanced their gait is, and how upright their posture is, allowing them to better understand their physical health, as well as to set and evaluate health goals or fitness goals. Now, subcomponents might be the telemetry subsystem, the communication subsystem. When we first design and launch systems, they're at their best. Everything is very clearly defined, or as clearly defined as it ever will be. And the systems are well architected. They're cleanly implemented. They have a clear purpose to support the goal for which the system was intended. Over time, each system will become overcrowded. New features will be added, functionality might degrade or change, and the system fractures as it supports more use cases. And this is the origin of Hiram's Law, which you'll find at hiramslaw.com. And what it says is that users of a system will become dependent on every available behavior of that system, whether it's documented or not, whether or not it's available through an API. So once clients rely on this scope, it makes it very hard to walk back. And we found that to be the case during our Moonshot migration, that there were behaviors within the storage system that clients were building entire features of their own around. If these were not features that were designed to be exposed to the outside world, it was or to the other applications within Google, it was unintentional. And so unwinding those behaviors was a significant amount of effort on the project team's part. So both writing down in an accessible and visible location what your system will do, as well as providing a clear and well-documented application programming interface or API, and then restricting client use to that API will make a purposeful system. Now, step back. What would make this not a purposeful system? Let's say that we took the G shoe and added message sending capabilities. So we tacked on SMS to the shoe or from the shoe. And that would be great for social networking among GShoe members. It would, however, make the system's purpose less coherent. Is this still a telemetry-enabled wearable, or is it a social networking tool? You want to have purposeful turtles all the way down. Additionally, each level of abstraction should define its own purpose from the overall system to server nodes to individual APIs. This helps clients use our system as intended, as well as guide internal development. And for very practical purposes, the documentation can be used to define alerting and SLO, or service level objective strategies. To sum up, a purposeful system is very similar to a microservice in that it does one thing and it does it well. It has well-defined boundaries. It provides documentation both to the human reader and to other programs through an API. You can see an example of all of this on the screen for the shoe, which is on the left in that very elegant box. Now we can understand what to do with these patterns. We have discovered and classified patterns through observation. The real value of these patterns is what you take and build with them. Patterns are similar to Lego blocks in a way. They are pre-built pieces. They're ideas of software that can be quickly assembled. You can build a circuit breaker, you can build bulkheads, and you can place them into something that's a strong structure with enough shape to allow rapid prototyping and composition. And as with Lego, the possibilities are endless. Some things that you might build might look really weird, they might not balance. Again, you need to bring judgment and experience to how you put these components together. And you might also find them used in the wrong way. Adding a proxy before understanding where demand takes place in a system obviates the use of that proxy. You probably want to allow room for a proxy in a system or a cache, but not add it until you understand how that system behaves in production. Now, there are tools and platforms that exist to ease your path for using these patterns. There are building blocks such as gRPC and Kubernetes, and these embody a lot of the practices that we've seen, including half-sync, half-async, and graceful degradation. Patterns can be primarily technical, like half-sync, half-async. Patterns can encompass organizational as well as technical concepts, such as the strangler fig. Some patterns guide how you develop with other patterns, such as the purposeful systems. Some patterns will work in concert with each other, such as the bulkhead and circuit breaker patterns. Each contributes in its own way to the overall reliability of the system that you are building and to the management and operation of the digital service that you're providing. Having a shared vocabulary of patterns helps you connect with your teammates who are an essential part of the socio-technical system of building software. In many of the preceding slides, we talked about traffic patterns and request flow. Now I want to emphasize that we are connecting people through patterns. You and your teammates can communicate, discuss, and share the ideas about how to build systems through the language of patterns. Having an understanding of patterns, that they exist, that you can intentionally use them in your systems, becomes especially valuable during systems design. Documenting the systems design and the purpose of that system also allows the next generation of developers, whether they're 6 months from now or 6 years from now, to build on and operate your system. And the professional environment in which many of us work mean that we are collaborating in teams rather than writing code in isolation. Having a pattern language, to borrow Christopher Alexander's title, allows members of the team to discuss problems and potential solutions. Patterns provide a shared vocabulary for building these systems. So I hope these patterns have been interesting to learn about. However, the most important thing I want you to learn today is how to think in patterns. This way of approaching our systems, both to learn from them and to improve them, is a very powerful point of view. Now, if you can discover and apply patterns, then these discoveries can advance not only your local teams, but your whole organization and your whole company. It's a very powerful way to rapidly build, deploy, and operate reliable systems. that's the prepared material. We'll take a brief pause so I can clear my throat and have a drink, and then I'll answer questions for the next 15 or so minutes. Thank you very much.
Perfect. Thank you very much, Salim, for such an insightful session. I request all the participants, please drop your questions so we can take it from here. Right. So until then, I have a questions which we have got across a live platform. So Salim, let me know when we can start with the Q&As.
Let's start now.
Okay, great. Perfect. Just give me a minute.
Okay.
All right, so I can see a question we have got from Kuldeep. He's asking, what's the most common scaling bottleneck you have seen in distributed system, and how do you recommend teams address it early?
Well, the question was the most common scaling bottleneck that I've seen. And there's a two-part answer that comes to mind. The first part is understanding the relative priority of incoming requests, because not all incoming requests are the same, are as important as each other. There may be metadata or administrative requests. There might be user-facing requests. There might be user-facing requests that have different priorities. So the bottleneck there is treating all requests with the same priority. And we did that initially at Google. And we found that it led to bottlenecks. It led to resource contention. It led to timeouts on critical requests, which in turn had knock-on effects where we couldn't process subsequent requests because we had failed to correctly process initial requests. So we established a classification of different levels of traffic priority, as well as providing a way for specific methods to be tagged with different priorities. So that's one bottleneck, treating all requests the same way. And the other bottleneck is, how do I describe it? It's responding to requests that have been in the queue longer first, which is a FIFO, what's known as a FIFO, first in, first out strategy. This does not always work well, and in fact, often leads to bottlenecks. If there is some underlying and transient condition in a service, which leads to it not responding to requests for some duration. And then when the service returns to normal operating state, it tries to clear the oldest requests first. And this is a generally incorrect behavior because your system wants to respond to the newest request first. Old requests may be retried somewhere else in the system. They may be expired from the client. They may refer to out-of-date state. And so you'd process them only to find that all the work that you did was essentially useless. So the technique for clearing that bottleneck is to respond to the newest requests first, last in, first out, and gradually clear that queue. And a big part of making this happen, or actually not even allowing this bottleneck to occur, is to make sure that all requests through your system have timeouts so that they expire within the system after some fixed number of seconds or milliseconds. And that timeout can be set in the per request by the client. It can be enforced by the service that's receiving the requests, but making sure that you have both good request processing hygiene and that there are timeouts on all requests, those are important. So the two things that come to mind are traffic classification and timeouts.
Greatly answered, Salim. Thank you very much. So moving forward to the next question, we have got from Shruti. She's asking, from your work at Google, what's one reliability lesson that mid-sized organization can apply immediately without heavy tooling?
That's a great question. Thank you. There are a bunch of answers that come to mind. Okay, I'm going to give you a couple of answers. But the first one is to instrument your software. And this is under the heading of what's usually called observability, that you want to, as an engineer, as an operator, you want to have really fine-grained insight into what your program is doing. And using open telemetry to instrument the code itself can be extremely helpful, because then you can, there are many monitoring tools and frameworks that use open telemetry to aggregate information and show you both the common paths and outlier paths through your system. And this gives you tremendous insight into what's happening in a very large distributed system and what the requests are actually doing and for how long they're doing it as they flow through the system. So I think that instrumentation, especially with open telemetry or a similar tool, is something that you can do in an organization or on a project of any size. And it is not tied to any single platform or programming language. The other thing that you can do is to set caps on your auto scaling. So if you have auto scaling or automatic capacity management enabled for any parts of your system, whether they're being run through Kubernetes or you're doing them on bare metal, making sure that you set bounds on how many copies of a node or how many replicas of a service are spun up automatically will be very important to limit your costs in the event that something goes really wrong. Because something invariably will go really wrong, and you'll have hundreds or thousands of nodes of an expensive server running, and they're all going into cascading failure, causing more nodes to spin up. So that's something that is a few lines of configuration or a few checkboxes in an admin interface, and it will save you both time and a lot of money.
Great. Thank you very much, Salim, for answering this in very, in very detail. I believe, Shruti, you have received your answer watching us online. Thank you very much for the question. So we'll take last two questions we have got from Makaila, and then we'll stop with the Q&As, because we've already done with the scheduled time for the Q&A. In case if you miss any question or if you have more questions in your mind, please do reach out to our speaker. I've already shared his LinkedIn profile link in the chat box, so feel free to reach out to him. So yes, the Mikaela is asking what strategies can be applied to achieve predictive auto scaling in distributed system beyond reactive load-based approaches.
That is a good question, and it's a little tricky to answer, because beyond a load-based strategy, things get very dependent on your specific systems. And a load-based strategy should work well, especially if you're able to apply a little sophistication, so that the downstream nodes, which are receiving the load, are also reporting to the load balancers how much they're processing and how much additional capacity they have. And this is one of the benefits of having this bidirectional shared communication channel, is that you can pass load reports around. I'm sorry, I don't think I have a better answer than that. I really do think that load-based strategies are among the best. There are other methods. There are waterfalls, there are shared pools that allow you to do better load balancing and more active capacity planning, but they really depend a lot on specifics of your system. And this is one of those cases that that falls under a phrase that I used several times during the presentation, that you can apply patterns or strategies prematurely and then not reap the benefits. So I would say to examine your strategy once you've actually seen your system's behavior in production, and then decide, in addition to a load-based strategy, do you want to apply waterfall, where you might cascade from one bulkhead to another in order to provide additional capacity, or do you want to change the pool size, so increasing the effective capacity of a named set of backends? I'll also think about that and connect with me on LinkedIn, and I'll see if I can come up with something a little more detailed.
Wonderful. Thank you very much, Salim, for sharing your LinkedIn. Please feel free to reach out to him. Okay, we'll be taking this question as the last question for today. So, how can observability pipelines, metrics, logs, stresses be architected to remain fault tolerant and cost efficient at planet scale traffic volumes?
All right, this is a good one. So the short answer is I don't know. But the better answer is there are people who do know, and they've studied this problem and implemented solutions in products and services. And I think most cloud providers do this well. And there are also companies like PagerDuty and Honeycomb. And to be fully transparent, I know and have worked with people at most major cloud providers as well as at PagerDuty, Datadog, and Honeycomb. They build systems that do exactly this. They've studied the problems, they've understood the challenges, and they've built the pipelines. So by using one of their tools or platforms, you can have really cost-efficient observability, and you can collect metrics and traces, and you can do it in a pretty cost-efficient way. And these platforms can be really very good at it. And part of the reason I don't know was my initial answer is because I've sat next to teams at Google that did exactly this. I didn't work directly on them. I built the storage systems that were where they stored all of the observability data. And it's a big project to do this on your own because you have to build the right kind of data store, which is usually a time series database, but now there are even more efficient solutions. So you have to build the right kind of data store. You have to manage that data store efficiently. You have to know, in addition to what kind of metrics you're collecting, you have to control metrics collection frequency and retention volume all the way from the application down to the storage. It's a big problem that you're asking about here. And I do think that the best answer is to use one of the solutions that exist. Because otherwise you're going to invest so much in terms of engineering resources in solving this problem, you might distract your company from its original business goals.
Wonderful. Thank you very much, Salim, for answering all the questions. Again, if you miss any question, feel free to reach out to our speaker. We have already shared his LinkedIn profile link in the chat box. So yes, before I could proceed further, would love to hear final thoughts from you, Salim, for all our participants today.
Yes, thank you. I'm really grateful for the questions. They're provocative, hearing what you all are thinking about. And I think the key takeaway I'd like to leave you all with is we talked about patterns that exist in the literature, some patterns that come from my own experience at Google that like purposeful systems and graceful degradation. These all exist to provide you as software engineers a way of building better systems that are more reliable, that you can operate more efficiently because you have a common vocabulary that describes some of these components and their known solutions. So what you should hear from all of this talk about patterns is that there's a language of patterns that you as engineers can build on as you move forward solving new and interesting problems of your own. I do encourage you all to connect with me on LinkedIn. Let me know that you attended this session, and I also welcome more questions about any reliability engineering topics. Thank you very much.
Wonderful, Salim. Thank you very much for such a wonderful thoughts. And yes, earlier, as I mentioned, that we do have some great announcement for all of you. So this is regarding the certification that is related to today's featured session that we had, GSDC Certified Learning, Elevating DevOps, DevSecOps, and SRE for Next Generation Reliability. So you'll find all the certification that GSDC has for all of you. You can opt out for any of the certification which is mentioned over here. You can check our website to to get more details regarding this certification, you can opt out for Certified Site Reliability Engineering Foundation, Certified DevOps Foundation, Certified DevOps Practitioner, and Certified DevOps Foundation. We do have these certifications. So as you all know that these certifications are lifetime validated certification, which comes along with the learning resources, where you'll be getting a lifelong learning, which comes along with the learning flexibility. Also, you'll be having chance to connect with our training partner channel to get information regarding the training program in case if you're looking for any. Also, you'll be having an opportunity to work on the capstone project. That is something you'll get a chance to work on the real time simulation practice. So to grab this opportunity, you can use this promo code, which is DevOps20, to get an amazing discount. This is only for our webinar attendees. Also, would love to introduce the new concept that GSDC has come up with, utility tool. So with this tool, what you can do, you can improve your LinkedIn profile score. You can build your personal brand. You can use this tool with 100% off. This is only again for our webinar attendees. You can use this August 100 promo code, and you can use this utility. You'll find the link in the chat box. I've shared it earlier. If you want, I can share it again. So yes, would love to inform you all. Tomorrow we'll be having a second session of this series. We'll be having Rod Anami with us. He's a SRE coach at Kindriel, and he'll be presenting the topic that is balancing reliability and feature development in SRE. So please do join us. That is happening on 9th September 2025 with the same time slot, that is 8:30 a.m. CST. As you must be aware of the panel that we have for this AI tool, that is we are running for 28 days. So we have this amazing panel of AI expert aligned for this AI tool challenge for 28 days, which is started from 18th August, and it is happening. We've already done with the 15 challenges. So if you want to unlock your AI skills potentials, please do join us for this AI tool challenge series, which happens usually at the second time slot, that is 11:30 p.m. SGT, exact after 1 hour. You can join us. Also, you can refer your friends and colleagues to this session, and by doing that, you can earn rewards that is worth $400. And remember one thing: referring people to knowledgeable session, you're already becoming a thoughtful leader, and by doing that, you can enhance your credibility. Also, top 3 winners will be featured on the GSDC Wall of Fame. I would like to show you all how the leaderboard looks like, where you can see your points that you have earned so far by referring maximum people. Just allow me a minute. Here we are. So you can access our event web page where you'll able to see the event details. And if you scroll down a little bit, you will able to find a search bar here. Right, leaderboard legends, you will able to see the search bar. Here you can put your name and you can see how much points that you have earned so far by referring maximum people. If you earn 50 points or more than 50 points, you are eligible to get the rewards from the GSDC, and top 3 winners will be featured on the GSDC Wall of Fame. So do refer maximum people to our sessions and be a winner. So coming back to the main slide, here we go. So okay, so we do have these 3 winners, and I would love to congratulate to them. Would love to congratulate to them because they have topped at our leaderboard by referring maximum people so far to this session. So you still have a time, because we'll be announcing all the winners at the end of this week, end of this session. So please do refer maximum people that you can. Also, if you want to be a speaker at our GSDC session, you can reach out to us. As we do have a platforms like Learning Capsule, webinars, and the podcast. Also, we'd love to connect with you all over the social media platform. You can scan this QR to get in touch with over the LinkedIn. You can explore our website, that is www.gsdcouncil.org, to check offerings that GSDC has for all of you. And you can connect with us over the WhatsApp group to get daily update on the events and the webinars that we do have. And at last, do not forget to share your session takeaway and the learning outcomes on the Trustpilot. You'll find all the links in the chat box. So check it out. And thank you very much for joining today's session. I hope to see you all for the next session as well. Until then, keep learning and take care. Thank you. Thank you, Salim. Bye-bye, everyone. Take care.